In recent years, a powerful statement has circulated across social media, educational posts, and history blogs. Alice Parker invented central heating in 1919. It's a sentence that lands with impact. It highlights a black female inventor at a time in American history when very few women, especially black women, were granted federal patents. It sounds like a long overdue correction to the historical record, and in some ways it is. Her name deserves to be known. Her patent deserves to be discussed. But the way that sentence is often presented flattens a much longer timeline. Central heating did not begin in 1919. At the same time, dismissing her contribution because heating existed before her would also be inaccurate. This is not a story about replacing one narrative with another. It's about understanding where she fits in a chain that stretches back more than 2,000 years. When we slow down and walk the timeline carefully, something more interesting appears. Not a myth, not a debunking, a layered evolution. To understand where Alice Parker fits into history, it helps to step back much further than most people expect. Central heating did not begin with pipes, radiators, or gas lines. It began with stone, fire, and airflow engineering more than 2,000 years ago. Around the 1st century BCE, Roman engineers developed what is widely recognized as the earliest large-scale central heating system, the hypocaust. This system was not a primitive fireplace scaled up slightly. It was an intentional structure integration of heat movement into architecture itself. A hypocaust functioned through a carefully designed subfloor chamber. Builders constructed floors on top of dozens, sometimes hundreds, of short stone pillars known as pillae. These pillars created a hollow space beneath the floor surface. A wood-fired furnace positioned at one end of the structure pushed hot air into this cavity. As that hot air traveled beneath the raised flooring, it heated the thick stone slabs above. Those slabs absorbed and radiated warmth upward into the room because stone holds thermal energy. The system created a relatively stable and sustained heat output rather than short bursts of warmth. The design extended vertically as well. Hollow rectangular clay flues called tubuli were embedded within interior walls. As hot air moved under the floor, it also rose through these vertical channels, warming the walls and helping to circulate heat more evenly throughout the space. The airflow then exited through roof vents, creating a convection cycle that continuously pulled fresh hot air from the furnace below. Roman bathhouses relied on this design to maintain multiple rooms at different temperature levels, including warm rooms and extremely hot chambers. Workers constantly managed the furnace to regulate heat intensity, demonstrating that even in ancient times, temperature control and airflow management were understood as adjustable variables rather than fixed outcomes. This was central heating in its purest definition, one heat source deliberately distributed through architectural design. It required engineering precision, material knowledge, and labor coordination. It was expensive and limited primarily to public bath complexes and wealthy homes. But the underlying principle was firmly established. Heat could be centralized. It could be directed. It could be structured into a building itself. When people imagine central heating as modern innovation, they often overlook how sophisticated Roman thermal engineering truly was. The concept did not begin in the 20th century. It began with stone floors elevated on pillars and hot air moving intentionally through walls. After the decline of the Roman Empire, large-scale centralized heating systems faded from widespread use in Europe for centuries. Most homes returned to fireplaces, hearths, and eventually iron stoves. Heating was localized again. It was direct, immediate, and often inefficient. Entire rooms would remain cold while a small radius near the fire grew uncomfortably hot. Smoke management was inconsistent. Fuel consumption was constant. It was not until the Industrial Revolution that central heating re-emerged as a practical necessity rather than a luxury feature. In 1793, English engineer William Strutt implemented one of the earliest documented steam heating systems inside a cotton mill in Derbyshire. Textile mills were vulnerable to fire due to the presence of cotton fibers suspended in air and wooden structural supports. Open flame heating posed constant danger. By relocating combustion to a central boiler and distributing heat through sealed metal pipes, Strutt reduced fire risk while also heating large interior spaces more consistently. Steam heating operated on thermodynamic principles that were only beginning to be fully understood at the time. Water heated inside a sealed boiler converted to steam, expanding rapidly as it changed phase. That steam traveled through a network of iron pipes into radiators or heating chambers positioned throughout the building. As steam cooled, it condensed back into water, releasing significant amounts of latent heat during the transition. The condensed water then returned to the boiler, creating a closed-loop system. By the mid-19th century, two primary heating systems dominated large buildings: steam systems and hot water systems. Steam systems operated at higher pressure and moved heat quickly but could be noisy and difficult to regulate. Hot water systems circulated heated liquid through pipes, offering more gradual but often more stable temperature distribution. Cast iron radiators became standard fixtures in multi-room structures. Their ribbed and columned design maximized surface area, improving both radiant heat emission and convective air circulation. Central heating was no longer rare by the late 1800s. Apartment buildings, schools, hospitals, and affluent homes across Europe and the United States relied on boiler-based systems. However, these systems were fuel-intensive and typically powered by coal. Coal required manual loading, produced soot and ash, and demanded regular cleaning. Temperature control remained limited. Entire buildings were often overheated because systems were difficult to fine-tune on a room-by-room basis. Heating technology had advanced significantly since Roman times, but it remained imperfect. Engineers were solving problems in stages, responding to the materials and energy sources available to them. By the end of the 19th century, central heating was functional, but it was ready for refinement. The turn of the 20th century introduced a major transformation in American urban infrastructure. Multiple gas lines, originally developed for street lamps and commercial lighting, began expanding into residential neighborhoods. Natural gas presented a cleaner burning alternative to coal and wood. It produced less soot, less ash, and allowed for more consistent flame control. The fuel itself could be delivered through pipes directly into homes, reducing the physical labor associated with hauling and storing solid fuels. However, incorporating natural gas into a centralized heating system was not as simple as changing fuel type. Coal furnaces operated differently from gas burners. Gas combustion required controlled air mixtures to maintain efficiency and safety. Ventilation systems needed to prevent carbon monoxide buildup. Heat exchanged surfaces had to be designed to withstand sustained combustion without degrading. This period marked a transitional phase in heating technology. Steam systems still dominated large buildings, but engineers began experimenting with gas-fired furnaces that heated air directly, rather than relying exclusively on water or steam as a transfer medium. These systems began to resemble the earliest iterations of forced air heating, though mechanical blowers were not yet widespread. Homes in the early 1900s frequently experienced uneven heating. One room might be warm while another remained cold. Temperature regulation was often crude, relying on manual damper adjustments rather than automated thermostats. Engineers sought ways to improve air distribution rather than merely increase heat output. It was within this context of fuel transition, combustion redesign, and airflow experimentation that Alice H. Parker filed her patent in 1919. She was working at a moment when gas infrastructure existed, but heating systems had not yet fully adapted to its potential. On December 23, 1919, Alice Parker was granted United States Patent number 1325905. The document itself is not symbolic or speculative. It is a formal federal record detailing a proposed gas-fired heating system designed to improve indoor temperature regulation. The air distribution, when examining the patent closely, what becomes clear is that Parker was not merely suggesting a change in fuel source. She was proposing structural improvements in how heat moved through a building. Her patent outlines a furnace system that utilized natural gas burners housed within a combustion chamber. At the time, many residential heating systems still relied on coal-fired furnaces or localized heating stoves. Coal systems required regular refueling, produced ash and soot, and often generated uneven heat because of inconsistent combustion intensity. Gas, by contrast, allowed for a more controlled and continuous flame. Parker's design leveraged that controllability. But the most notable aspect of the patent lies in its airflow management. The documentation describes a series of ducts arranged to distribute heated air to various rooms in a building, rather than allowing heat to radiate passively from a central stove or depend solely on steam traveling through pipes. Her system directed warm air intentionally through branching channels. The drawings included in the patent show compartmentalized sections within the furnace structure, designed to capture heat and funnel it to controlled pathways. This reflects a conceptual shift from radiant heat dominance towards structured air circulation. Radiant systems heat objects and surfaces directly, allowing warmth to spread outward from a fixed point. Forced air systems, which would later become common in American homes by the mid-20th century, rely on moving heated air through ductwork to achieve even distribution. While Parker's systems did not incorporate modern electric blowers, the architectural concept of directing heated air through ducts aligns closely with that later development. The patent language emphasizes efficiency and evenness. It describes regulating airflow to avoid overheating certain areas while leaving others cold. Early 20th century homes frequently experienced this imbalance. One room near a furnace might become excessively warm, while distant rooms remained uncomfortable. Parker's design attempted to solve the problem through structured distribution rather than simply increasing heat output. Another important element is combustion placement. By enclosing gas burners within a defined chamber and routing air around that chamber before distribution, the design suggests an early understanding of heat exchange principles. Modern furnaces operate by passing air over a heat exchanger heated by combustion. Parker's proposal demonstrates a similar awareness that heat should be transferred to air within a contained environment before being distributed. It is important to note that there is no confirmed evidence her specific system entered commercial production or widespread installation. This does not diminish the patent's value. Many patented systems remain prototypes or conceptual designs that influence later developments indirectly. Patents function as documented contributions to engineering discourse. They mark points where inventors formalized ideas, submitted them for federal review, and secured recognition of originality. In the broader technological context of 1919, Parker's design appears during a period when gas infrastructure was expanding but heating systems had not yet standardized around modern forced air configurations. Electric motors capable of reliably powering blower fans were not yet common household fixtures. Building codes and ventilation standards were still evolving. Implementing a gas-powered ducted air system would have required significant structural adaptation in existing homes, which may have limited immediate adoption. However, when viewed through a long historical lens, her patent represents a bridge. It sits between coal-fired radiant systems of the 19th century and the gas-forced air systems that became widespread decades later. It reflects awareness that fuel efficiency, combustion control, and airflow management were interconnected challenges. The significance of patent number 1325905 lies not in claiming the invention of central heating, but in documenting an early 20th century attempt to modernize it. It captures a moment when heating technology was shifting from heavy, manually fed boilers toward cleaner fuel controlled systems with improved distribution logic. The patent stands as evidence of technical engagement, forward-thinking design, and participation in an evolving engineering conversation. It records that in 1919, Alice H. Parker was not merely observing the heating systems of her time, she was proposing how they could be improved. When modern posts state that Alice Parker invented central heating, they compress centuries of engineering into a single date. That compression is understandable but incomplete. Central heating existed long before 1919. Roman hypocaust systems, steam boilers, and radiator systems were already established technology. At the same time, dismissing Parker's contribution because she did not originate the concept of central heating would be equally misleading. Engineering history is cumulative. It advances through iteration, adaptation, and refinement. In 1919, women accounted for a very small percentage of patent recipients in the United States. Black women represented an even smaller number. Securing patent number 1325905 required technical literacy, design capability, and successful navigation of the patent system's formal submission requirements. The patent office demanded written specifications, claims outlining original contributions, and detailed technical drawings that met federal standards. Her accomplishment was not symbolic, it was procedural. It was technical. It was documented. Recognizing her contribution accurately does not require inflating her role beyond what the historical record supports. It requires placing her correctly within the timeline of gas furnace development and airflow management during the early 20th century. Accuracy strengthens recognition. Alice H. Parker did not invent central heating from nothing. She did something different. She contributed to the modernization of heating technology during a period of energy transition. She secured a federal patent for a gas-powered furnace system with managed air distribution in 1919. Her design aligned with concepts that would later become standard in forced air heating systems across the 20th century. She was part of the progression, not the starting point, not the sole architect, but a documented contributor during a critical shift in domestic energy use. History is strongest when it acknowledges every link in the chain honestly. Roman engineers built hypocausts. Industrial innovators developed steam systems. 19th century inventors refined radiators. 20th century engineers advanced gas furnaces and airflow systems. Alice Parker belongs in that timeline. Not inflated, not diminished, placed correctly. And when you understand the full arc from ancient stone pillars to modern thermostats, the real story becomes richer than a single viral sentence ever could be.